Let me get myself on the screen here. So we've talked a little bit about trees, and I go like, well, what am I going to use them for? Well, one of the things you're going to use them for is they're a great way of organizing data to search for information, to quickly get through a lot of information. Have you ever tried to go through a linked list and find the 6th item out of 100 or the 94th item out of 100? And binary search tree says, hey, I can find a way to organize this data in such a way that we can shorten that search time. So what we're going to do is we've talked about binary trees. So now we're going to look at how to create a binary search tree and then look at how they're used in several different areas. Now, I'm not going to ask you to write any C code, but we will look at some of the algorithms. So hopefully this give you an idea as to how trees and binary search trees in particular, because next chapter will be on, I think it's AVL trees, another method of using trees in way to shorten interval to find data that you're looking for. So let's go see what we can do through. So now remember, so the binary search trees, they're excellent in searching a list that has some sorting capability to it. Now, there is a cost with inserting and deleting data, but when you add the cost of searching, if you're going to do it a lot, the addition and subtraction costs are well outweigh the organization to go to a search tree. So some of the properties of a binary search tree is all items in the left subtree are less than the root. All items in the right subtree are greater than the root. And each subtree in itself is a binary search tree. So every time you add or delete an item, you want to make sure that these three properties are maintained. So the left are less, the right are greater, and all subtrees have to be binary. So just a picture is definitely worth the 1,000 words I just said. So you got your root node K, wherever it went, my root node K. So anything to the left have to be less, anything to the right have to be greater. So let's look at some valid binary search trees. Here you've got a single node. Is it a valid search tree? Yes, because what I have, everything to the left, there is nothing to the left or to the right, so I still have valid, even though it's the most simplistic, but when you create that first node, it's okay. Here's your second example. So you got your node, anything to the left is greater, is less than here, because I got to look at which way I'm looking at the graph, but I'm looking at it, so it's on my left, and hopefully when you're reading the book, it's on your left. But you got the node, anything less than the node goes to the left, anything greater goes to the right. Now, when I look at this and go, wait a minute, this doesn't have a nice tree shape, that is true, but the properties still apply, that anything to the left is less, anything to the left is less. Even though there's nothing greater than those, it is still a binary tree. Here you've got an example here. It's like it meets all the properties, all valid. So everything to the left is less than, everything to the right is greater. Applies across the board. And the same thing applies for this one. It's just pretty much the reverse opposite of example C. Now, let's look at ones that are not valid. Here you've got item A. Here you got 17, 22, and 19. It says, well, if anything to the left has got to be, whoops, it's not less than. So that means I'm in violation of that less than rule. I got the greater than rule off of 17, but I do not have the less than rule. Now to convert that back, where would this 22 have to be? The 22 would have to be down here under these 19. But in this case, it's an invalid one. Here, what do I have? I got 17. I've got, my 11 is less than, so I can't put it to the right of that right node. It's got to go off the left. So it should have been down. It should have been 17, 11, and 6. Here you're looking at, okay, I've got 17, 6. Okay, that one's less. That one's greater. Okay, that's good. Oops, I go down a layer, and now I've got, that one's not less. I've got to maintain this subtree has got to still be a valid binary search tree. So everything I put underneath this node 6, has to still apply. So with these numbers, then they should be under what? I should have been under 19, should have been here. 11 should have been here, and 15 should have been here. Again, what do I have here? This 22 probably should have been, when it was inserted, should have been put under the 19. So 3 basic rules. Just keep them in mind, because one of the couple of homework assignments is giving a set of numbers. You're going to create a binary search tree. Now, okay, I've got it created. What are the things I can do with it? Well, one, I can traverse it. I can search. I can insert, or I can delete. Some of these are straightforward. Some of these take a little bit of thought. Now, traversal, we've done what? We've done a pre-order, in-order, and post-order. As far as when do I process that central node, that root node? Well, in binary search tree traversals, in-order traversal produces a sequence list. So that is very key when you're dealing with binary search trees. So just keep in mind that in-order traversals give you that sequential list. And in most cases, that's kind of what we're looking for, because you're trying to get through the list as possible. So you want to get to a point and make a decision relatively quickly is in searching for that item. So let's look at searches. Now, granted, there are 3 basic search algorithms. One, I want to find the smallest node, I want to find the largest node, or I want to find a requested node. So to find the smallest node, what I do, I keep following all the branches until I get to a leaf. So follow every single left branch until I get a leaf, and that will be your smallest node. Because remember, everything to the left is smaller than its parent. Now, the largest node, you follow all the right branches until you get to the leaf. Now remember, leaf is the last node where there's no, both links to left and right are null. That makes it a leaf. So you follow all the right branches, get you the largest node. Now, to find a requested node, you've got to basically make a comparison. When you get to a node, you got to make a comparison, and then you're going to move left or right based on if it's greater than or equal to than the desired value. So let's we'll use this binary search tree, and let's just make sure it is a binary search tree. What have I got? I've got here's my notice. That was 18 is less than 23. That's correct. So is everything to the left of this greater than 23? 1, 2, 3. Yep. Everything's greater than 23. Is everything to the right of it less than 23? And the answer is no. So this tree, and if you look at 18, 12 is less than, it's on the correct side. 20, it's on the correct side. Same thing with 35 and 52. So this is a valid binary search tree. It's also a full binary search tree because what? I have all my leaves populated. Okay? So let's look at, like I said, the smallest, relatively simple. What am I going to do? I'm going to take the left tree. If it's empty, I go ahead and return the root because I don't have anything. I've gone to the bottom. If not, now you start seeing the use of recursive code. I'm going to call the find the smallest again, passing the left subtree. And I'm just going to keep following that all the way through until I get to an empty left subtree. And then return that answer. So, see if the picture makes sense. I got, left tree's not empty. Go down to it. Left tree is not empty, go down to it. Left tree is empty, guess what? I'm returning 12. So the smallest node in our chart is item 12. So we kind of slowed up here, and you look at this, yep, 12 is the smallest number that we have in this example. Of course, finding the largest node, what am I doing? And now I'm following the right subtree, doing the same thing. So again, I'm going through. Now, so largest and smallest, relatively easy. I'm going left or I'm going right. Now, the question is if I'm searching for a given value. So right now, we've been taught a couple of different ways of organizing data. One is an array that you've probably used since computers, your intro to C++ or Java. How do you store information? You store it in an array. Based on how you're using it, you may want to store it in a sequenced array, so the numbers are increasing or decreasing in value. So if I look at so if you look at the ways those two structures are organized, now what could you see as far as inserting or deleting in an array? Can you see some issues? If I want to delete the number 23 here, and I still got to make this a sequential list, what do I do with all of these numbers? What happens if I'm looking for the value 44? What do I have to do? I've got to go through 1, 2, 3, 4, 5, 6 items of comparisons to make sure to find that one. In a binary search tree, I'm making one comparison, moving down, make another comparison. I've got a match. I'm done. So the amount of processing time for searching for an algorithm can be substantially less. So let's take a look at the algorithm here. So we're looking for, we're given a binary search tree, and we're looking for a target key, an item we're searching for. And then I'm just going to return that the value is found or not found. So if the tree is empty, it's null, I'm done. Just return, not found. But if it's a full tree, now I'm going to do a comparison on that target key, compare it to the root. Is it less than or greater than? If it's less than, I'm going to follow the left subtree, and I'm going to search that. So here you're seeing that recursive code again. Makes it very simple to write this algorithm using recursion. So hopefully the more times you see it, the more you're going to say, hey, this is a good idea and to keep in your toolbox in your programming history, future careers. Compare that. If it's greater than, I'm going to the right, and if not, we're going through. So here's just a quick example of this. Is what am I doing? I'm looking for the target, looking for the number 20. I look at the root node, I can make that comparison. I'll go left or right. Since I'm looking for 20, it's less than 23. I'm going to the left subtree. I make the next comparison, greater or equal to. It's greater, so now I'm going to the right tree. Once I do the match, I return that value. So you see, recursion ends up being a very simple, very nice way of implementing this algorithm. Now the trick becomes is when I do an insertion or deletion, I want to make sure that the order, the structure has to be maintained. So I've got to make sure that when I'm adding data to a binary search tree, I want to make sure that what I want to do is I want to follow the branches to get to an empty subtree and then insert that node. Now, if you allow for duplicates should appear in the right subtree. So Here's just a brief example. We had a tree, looks like the same one we had a few slides ago. We're going to insert 19. So what I'm going to do, I'm going to make a comparison to 23. So it's less than 23, go to 18. Whoops. 19 is greater than that, I go to the right. It's less than 20, go to left. So I'm looking for that first element, that first leaf that's lower, and then I go ahead and add that. If I wanted to add the number 38 to this list, what do? I compare 38 to 23, it's greater. It's less. It's greater. So all you're doing is you're following the tree down, looking for that leaf node that follows the pattern, whether it's greater than or equal to its parent. So insertions are relatively straightforward. Now, here's the code a little bit. So you got an empty tree, set it to new node, return. If the new node is set, I'm going to call the left subtree or the right tree subtree. All it is making a comparison and then following the right tree until I get to that that leaf node, and then insert that. And here's just a rough idea of how to go through trace it. I'll let you go through and make sure that makes sense to you. I think I talked you through it a slide or two ago. Now, deletion, there are several different cases that need to come into play. One, if there are no children, go ahead and delete it. No big deal. If there is only a right subtree, delete the node and attach the right subtree to the parent node. Or if there's only a left subtree, delete the node and attach the left subtree to the parent node. Now, those three are fairly straightforward. Now, if there are two subtrees, so that both the left and right subtrees exist, now I've got to make sure I take care that I don't cause what they call an unbalanced tree. That means I've got too much data going the wrong side, and I want to try to maintain the structure as possible. There's a couple of ways of doing this. One, you can find the largest node, and then you can delete that node and move the data to replace the deleted node. Or you can go find the smallest subtree, right subtree, and then move the data. You're looking at me like, what is he talking about? Well, let's just take a look at, let me just see if maybe it make more sense to do this first. Is if I want to delete, I'm going to delete the number 23 from our list here. So what I'm going to do, compare this, it's not that, it's greater than, go here, whoops, now I have a match. So this is the node I want to delete. I want to delete, whoops, I want to delete 23. So what do? I can either go, I follow all the way down, find the largest key on the left, what's the largest one on the left subtree, move this to the one that's being deleted, as you can see here. So now I've got basically two copies of 22, and then delete 22. Delete that largest node. Let me slide out of the way. So you find the items you're going to delete. You follow to get to the largest one, the largest node. Copy it, move it to the node you're deleting. That's what you got here. Now I got two copies here. And now go back and delete the one you copied. So let's see if the algorithm makes sense here. So one, if you got an empty return, return false. I couldn't delete the node you wanted it to. But if the delete key is left, I'm going to call the left subtree, or if it's greater than, I'm going to call the right subtree. Now, if the node is found, if that delete node is found, now you want to, first thing I want to do, I want to test to make sure if it's a leaf node. If it's a leaf node, go ahead and delete it and you're done. no big deal. But if there isn't, you got to, there's no left subtree, you got to make the right tree the root and return. If the node to be deleted is not a leaf, I got to find the largest node on the left. I got to save it. Set the largest there, and then move that data, and then I can go back and delete the left subtree node that is being. So it's kind of it's not overly complicated. It's just like I'm looking for the node to get deleted. I'm going to find the largest left subtree, copy to the node I want to delete it. So basically what did that do? That really eliminated 23 from our linked list, but it gave me a duplicate copy. So here I got duplicates here of 22, and now I just got to get rid of that node. So, and you could have reversed this and said, I want to find the smallest value, but this way it works. Now, I'm briefly going to touch on, this is section 7.3, is a lot of the C code. I just wanted to give you a picture of what the data structure kind of looks like, because you've got your normal user program, and our abstract data structure here has some public functions, and then definitely some private functions that you want to make sure that only certain people can call. So just one of those things you want to keep in mind. Now, you look at this as well. I got a binary search tree. As I'm looking for items in here, it's possible that when I'm traversing that binary search tree, and it can be implemented in either recursion like we've seen, or using stacks. Now, stacks can be more efficient if the trees are traversed frequently. But stacks may require you to backtrack. You ever been in a maze and you get to a dead end and you kind of have to work your way back out? That's kind of backtracking, where I've got to go back. Whoops, I made the wrong decision. I've got to back up and go on to a different route. Another option is called a threaded tree. And basically that just says all null pointers are replaced to pointers to their successor node. And you're looking at me like, what? Now, the concept is that maybe it's easier to change this way here to show you a rough idea of what I'm talking about. You got a binary tree here, and of course we know you got left and right pointers, right? So it says here what? I'm going to replace null pointers with pointers of their successor. So we know B has null pointers here. So I'm going to take all of the null pointers, granted I'm going to say anything pointing to the greater, I'm going to take this left one and point it back to my successor. D, I'm going to point it back to a successor. What's a successor? Successor's A. And E, there is nothing there, so I'm not going to go through. So it basically says, hey, I'm going to make sure I can have an immediate thread back to who my successor was. By doing that, I don't have to backtrack. I automatically, because if I'm backtracking, I get here, what do I got to do? I've got to make sure I got save information, go back here before I can progress down. Now I just follow the thread or that link that was a null pointer and go follow it to my successor. Oops. So the concept is on the right subtree, the pointer can be empty, and you want to change the right pointer to the successor. So how do I build one of these things? You start with your binary search tree. You build it, adding items, look at the sequence, and put them in their correct order. And then I change all the null right pointers to point to the successor. question is, okay, how do I traverse such a beast? Well, I locate the farthest left node, and all I now have to loop through and follow the threads, the right pointer, to get to the next node in the sequence. So I have no recursions required and no stacks are required. So it can be relatively fast and not a lot of wasted energy. So it's just an interesting way of organizing data to quickly process things. Now, if you're doing a lot of insertions and deletions in your data, now this may be an application you don't want to use a threaded tree for, but it gives you an option. So just one more concept. So I'm just going to give you more and more tools as the semester goes on, as to you say, at least I can know these data structures exist. So when a problem arises, you can think about it and see how you want to apply them. Now, you went through that. Now, some of the assignments and problems and exercises, just so you can see the tree before you do it. Here's ones for, I think it's probably more than just exercise 10, but here's that example, and then figure for 10. So I think those are the only two. Whoops, I guess I did give you 12. So gives you a couple options there. Hopefully this helps you with the material in binary search tree. If you have any questions, let me know. Have a nice day. Bye-bye.